Hey AP students, we got a video here to do two things. Number one, determine the volts and amps, or the math, of each resistor in a complex circuit. Number two, determine how bright bulbs are relative to each other and what happens when you change the circuit. For part one, the math, we're going to use Ohm's Law, V equals IR, and what we know about what splits, what stays the same in a series of parallel to mathematically determine individual values in circuits. Here's our table we're going to be using. V, volts, amps, resistance, and if we need to, power, the number of resistors in the circuit here, and the total value down here. Now this is from a previous example. I put numbers in. You'll see a new example just right now. So here's our circuit. Ignore the water damage. We have 12 volts with a 3 ohm, a 4 ohm, and a 12 ohm as you see it. We're going to figure out how much current is in the 4, the 3, and the 12, and the voltage for each. If you don't mind, copy down this picture, leave some space, because our plan of attack is this table. Notice in red everything I observed so far. I know the total resistance, I know the total voltage is 12, and I know the first resistor is 3, the next one's 4, the next one's 12. The first thing we need to do is find the total resistance, Req. And to do that, I taught you how to draw these current arrows. So starting from the battery, we draw the current as letter I. It goes through the 3. And at this point, the junctions are split up into I1 and I2, two separate flows. I1 goes to the 4, I2 goes to the 12. At this point, they meet up again, and they reform letter I, the original current, back to the end of the battery. You could probably guess in this parallel circuit, I1 path has more flow than I2 because I2 has got more resistance. So looking at this, you've got to figure out what's in series and parallel with what. Well, we know that path I1 is parallel with path I2, and since they each only have one resistor, that means the 4 and 12 ohm resistors are also in parallel. If there were two things in this path, you would first have to say that they're in series, and their series combination is in parallel with the 4. So we have to mathematically solve for that resistance of the 4 and 12 in parallel. Now, you know the overall equation is 1 over Req equals 1 over 4 plus 1 over 12, and do 1 over that. But I also taught you this special thing. When there's two resistors, you can just do R1 times R2 over R1 plus R2. And no matter which way you do it, you get 3 ohms. I now taught you to draw another picture. The two parallel resistors have been replaced by 3. They are equivalent. And since I1 and I2 both started and ended with total flow I, the 3's got the same amount of current I going through it. Since both 3's have the same current, that must mean they're in series, so therefore the total is 6 ohms. So in my table I'm going to draw, and so are you, with VIR, I'm going to place all 3 original resistors here, 3, 4, 12. The total is 6 from the math we just saw, and the total voltage is 12. We could obviously figure out something from the other two. We know the current, that's kind of weird. The total current is going to be 2 amps. The 2 amps flows through both of them. So for the first resistor, 3, it has 2 amps going through it, and from V equals IR, that means it has 6 volts of the 12 going through it. Now again, in series, the total voltage of each adds up to be the total. Since there's a total of 12, and 6 is used for this, that means 6 is used for the 3. But remember, the 3 is really these two things in parallel, and in parallel, they share the same voltage. So I could also put 6 for the voltages of these two things in parallel. Now I can do V equals IR, and I find 1.5 and 0.5 for each. But I could have done another sneaky way as well. The 4 and 12. 4 plus 12 is 16. 12 is 3/4 of 16. 4 is 1/4. So since 12 is 3/4 of the resistance here, it has 1/4 of the current. Since 4 is 1/4 of the resistance, it has 3/4 of the current. 3/4 of 2 is 1.5. 1/4 of 2 is 0.5. So I could have done it either way, using logic through the voltages or using logic from the breakup. Let's check our answers. The current splits up. 0.5 and 1.5 is 2. Great, we did it. We just solved for the voltages and currents for each one. So now for the second part. We're actually going to have to be able to use our lessons of REQ and the math to show how bulbs compare and contrast. So here's kind of a cool question. Here is the same setup with 5 different bulbs, A, B, C, D, E. You can have a chance and copy this down and pause the video. If they're all the same resistors for each bulb, rank their brightnesses. Cool. To do this, I'm going to have you draw the current flow through each one. You could tell that I1 goes through A, I2 goes through B. It comes back to letter I. But then it separates. Now into I1 and I2 again, it's going to be different because these paths have different resistances than before. Now, which one of these has got the most flow? Well, it's going to be getting. If A and B are equal, that means they both have half the flow. So they're both half the current I, which means they're equal. But here, I3 has a lot less resistance in this path. So with the same flow, it's not going to wind up 50-50. More than 50% will go through I3, less will go through these two. So that means obviously that letter C has got the most flow since it has a higher proportion of the flow in this breakup. These two have less flow, and they have the same less flow because they're in series. So it's going to go more than 50% here. It's the highest. 50-50, these two are equal. And these two have less than 50%, which means they're equal in the end. So C is more than A equals B, which is more than D equals E. Ta-da! But hold on for a second. I created that circuit here. A, B, C, D, E. You can definitely see the results. C is definitely the brightest. These two are the same amount of brightness, but less than this one. And these two are also the same, but way less than any of them. So it works out. Now here's what gets interesting. What if there's a switch there and it opens up? We're going to figure out what happens to A and what happens to C. Now this is kind of tough, but here's what I want you to think about it. If this path gets open, nothing ever flows to it anymore, which means that this parallel resistance now just becomes a series resistance, which means the resistance of this part of the circuit goes up. You might be thinking, what, Jock, there's less now things in the way. True, but remember, each one's kind of considered separate. If you do the mathematics, when you take out a branch in a parallel, you get more overall resistance. So the overall resistance is going to go up, which means the overall flow is going to go down. So that of that less overall flow, these get 50% of that less flow. So A is going to get dimmer. But now that less flow all goes into C. It no longer splits up. So even though there's less flow overall, C gets all of that less flow, which means it's going to get brighter. So I'm going to say that A gets dimmer, C gets brighter. As proof, so here's the circuit. Before I want anything up, this current is 2.57. Half of it, or 1.29, goes through A, and 1.71, or more than half, goes to this. Notice what happens when I open it up. Close it, open it up. This one gets dimmer, this one gets brighter. So now there's 2 amps. Again, less current overall. This has half of that, which is 1. This gets all of it. So again, it's 2. But when it's on, it only has 1.71. Because even though there's more flow, a certain percentage goes through this part right here. So we just proven it. Good job.